Okay, we're going to try 2.4 outside of class examples. So the outside of class examples for 2.4. So here's the paper view. Um, and so this is our toolbox that we'll be using. I hope that you went and looked on Khan Academy and also in your textbook and saw the proof of this, that the limit as x approaches 0 of sine of x divided by x is equal to 1. It's actually not that easy to prove, and you have to have quite a few things up your sleeve to prove it, including the squeeze theorem, and then also you can also look at the proof of the limit as x goes to 0 of cosine of x minus 1 divided by x is equal to 0. So these are our things in our toolbox for that we're going to use in order to prove these things that they're asking us, these limits that they're asking us to prove. Of course, the idea isn't just to get the right answer. That's nice too. But the idea is to show work in a manner that makes sense. So one thing I want to add to the toolbook box right now while we're here is that also, so I want to add that the limit as x approaches 0 of x divided by the sine of x is also equal to 1. Now, the reason that it is because I can rewrite this to be the limit as x approaches 0 of sine of x divided by x raised to the negative 1, right? If I if I if I flip this, if this is being raised to the negative 1, then you would flip it over, right, in order to get it back to this. And so negative 1 means reciprocal is what it's meaning when you have a fraction. And so why this is good is because by my limit laws, the limit as x approaches 0 of sine of x over x, the whole thing raised to the negative 1, right? According to our limit laws, if you have your input that you're trying to take your limit of, that raised to a power, that you could raise the whole limit to the power. And why that is good is because now the inside is just this, right? And so this is equal to 1 raised to the negative 1. And you can certainly do that on your calculator if you like. 1 raised to the negative 1 is equal to 1. So I wanted to add in the toolbox that the limit as x approaches 0 of x over sine of x is also equal to 1. And I wanted to add that to my tools. Add to tools. Because that's going to come up on this problem here. Had it not been 1, I know that it was 1, but had it not been 1, and when you did this, when you had this raised to the negative 1, if you had a different number raised to the negative 1, then you would have had the reciprocal of it here. And so if you'd had 2 raised to the negative 1, that would have been half, which I know that's not what we had, but just so that you know that I wasn't ignoring the exponent of negative 1, even though the exponent of negative 1 got in this place. It's a little bit hard to see it, but I wasn't ignoring it. It's there. Okay, so here's the story that I'm trying to find this limit. And if I was to substitute in, I would get sine of 0 is 0. And pi times 0, I'm going to put parentheses around that, is 0. And sine of 0 is 0. So it's 0 over 0, which tells me that it's indeterminate. And that means usually when it's indeterminate, it's going to have an answer like half or 1 or whatever the answer is. And so I'm going to go find that answer, right? And so I noticed because it has sine in it, that I'm going to be using these tools that I have for sine. And I don't have sine of x divided by x, but if I did, then I would be able to use that tool there. And so here's kind of the idea. At the limit as x approaches 0 of sine of x, and I'm going to separate these, and then I'm going to put over here, I'm going to put a fraction, sine of pi x, like that. And so I split those apart, and we know that I will be able to use my tool right up here, if I just had the matching input, that input, whatever that is, it has to match in the denominator. And in this case, that's x. And up here in the numerator, now you just can't put an x down there in the denominator without making a balancing act. But I'm just going to put all the stuff that I need to put, and then I'm going to try to prove to you that I actually have a balancing act going. Whatever you have on the input, you need to put in the exact spot up here. And so they just need to match is what they need to do. So the input is x, but really they could have written this like this. The limit as whatever approaches 0, whatever's in there, of sine of the whatever divided by the whatever, it has to be the same, equals 1. You fill in the blank. And of course, that also goes for the limit as the whatever goes to 0 of the whatever on the numerator, and the sine of the whatever in the denominator is also equal to 1. So that's, the first one just was perfect, right? In the spots we had x, which is what we have here. But this one, what we're about to have in fill in the blanks, right? I have pi x here, so I want to have pi x right up here. So I'm going to put pi x right here. Now, I'm not done, but I wanted to first make sure that everyone was kind of seeing what my plan was here. And so I have physically put this x in the denominator and physically put a pi x in the numerator. And y'all know that if I put something in the numerator and the denominator, it's okie dokie as long as I put the same thing. And so right now, just looking at what I've put, in the denominator I put an x, and in the numerator I put a pi x, is what I have done, right? And so, and it would be okie dokie as long as I also put down in the denominator a pi, because that would be me multiplying by 1. And so I went out this maybe a little bit crazy, just saying this is what I need, and then now let me make it right? And so the x's are just fine because x divided by x is 1. So I'm going to put just out here to the side times 1 over pi, so that you can now see that what I put in the denominator was an x and a pi x. There it is. And in the numerator, what did I put? Well, I put the pi x. Well, I put the 1, I guess, but pi x is what I put in the numerator. So I have essentially multiplied here. I drug it apart a little bit, but essentially multiplied by pi x divided by pi x. And pi x divided by pi x is equal to 1. And so this should be left unchanged. And then this is how this is going to work. The limit as x approaches 0 of sine of x, because I can break them apart, right? Times the limit. Now I'm usually too lazy to do this. Now I want to make sure that, because remember I was telling you that it had to be going to the same place. And what we have here on this one is pi x. And so if x is approaching 0, what do you think pi x is approaching? So if x is getting really close to 0, what is pi times x getting really close to? So I hope you're saying that's getting close to 0 as well, and it is. So I have pi x here. And so it does match now in all 3 places, right? In all 3 places here, I have pi x, pi x, pi x, but I just wanted to make sure that you understood that I had that. And then here, times the limit as x approaches 0 of 1 over pi. Now by our toolbox, this is approaching 1. And this is approaching 1. And this is a constant, right? So this is approaching 1 over pi. So 1 times 1 times 1 over pi is 1 over pi. So we did a lovely job on that. And that would be a way that we could show our work really thoroughly so that everyone can see what we have going. We've improved the other thing, the one thing that we used to the -1. This is 56. and it's asking me to find this limit here. And I noticed that I have cosecant, and the cosecant is equal to 1 over sine. So I hope that you know that. So that this is equal to 1 over sine at x. And so I'm going to replace that in there because otherwise I'm not sure exactly what I have going. And so this is going to become the limit as x approaches 0 of 1 over sine of x times sine of x, not sine of x, sine of x. So its input is the sine of x. So now if I look at what I have going here, if I was to substitute into the numerator here, into the denominator here, sine of x, well, sine of 0 is 0. So the denominator is 0. And the numerator, the sine of 0 is 0. And then the sine of 0 is 0. And so it's 0 over 0. So that means I need to work harder. And I might not realize it, but I actually almost have exactly that theorem, right? Because that theorem is this: the limit as whatever approaches 0 of sine of the whatever divided by the whatever, right? That is equal to 1. And you see how I almost have that already because I have the limit. I'm not going to write where it's approaching just right now, but I just want to show you that this part's working, completely working without me changing anything, right? Because this is sine of x, sine of whatever in here, and then down here, the whatever. And what am I supposed to put in? What am I going to put in both of these? Well, I have sine of x and I have sine of x. And so I have that situation already going. And so the only thing that I would have to make sure of is that this is going to 0. And it has to be sine of x is going to 0. So if x is going to 0, so as x gets really close to 0, then what is sine of x getting really close to? So sine of x is getting really close to, so as x gets really close to 0, sine of x is getting, sine of 0 is 0, is getting also really close to 0. You might be able to draw your unit circle and convince yourself of that, perhaps. So here's my unit circle. And my angle is getting really close to 0, so I'm going to draw that out like this, like that. And so my angle is actually getting closer to 0. So my angle is getting closer and closer to 0. And this is the ordered pair down here, 1, 0, right? And the sine is equal to, when you're doing that, is equal to the y value. So as that angle gets closer and closer to 0, it's the height, y, right? And that height is getting closer and closer to 0 from both sides, right? So as the angle is a little bit, it's negative, and getting closer and closer to 0, well, the height, then the y value, the height here, is getting closer and closer to 0. So yes, this is true. That sine of as sine of x approaches 0, x approaches 0, sine of x is approaching 0. This is all set up, so this is just equal to 1. So here's some problems for you to go and try and see how you do on them.